Welcome, I'm Carl Tape. The previous video in the playlist was about earthquakes in Alaska. And this last one here is to say, how does this really happen? How do we really know where earthquakes are and how does this procedure work? So the focus is going to be on the Alaska Earthquake Center. The graphics, unless noted, are from the Alaska Earthquake Center website. There's endnotes at the end and the quoted text is from the AEC materials. Here are the basic steps in earthquake location. First, a seismometer in remote Alaska is constantly recording ground motion, always. These seismometers are also constantly transmitting ground motion recordings toward a data center at UAF. And this data center receives the real-time recordings of ground motion, computer programs. The Alaska Earthquake Center detects signals within the recordings. A set of detections is associated with an event or an earthquake, and an algorithm automatically determines an origin time, that is the time that the earthquake started, and a hypocenter for an associated event. Analysts then review the arrival time picks and hypocenters. This happens within minutes by a duty seismologist, and over the course of days, the staff seismologist gets the final solution for the hypocenter and origin time. So we'll start here with these first three topics. Seismometers recording, transmitting data. Basically, how does ground motion reach the Alaska Earthquake Center? For that, we want to start with one of the slides from the Alaska Earthquake Science Facts showing just this solitary station out, this one just over the border in Yukon territory, showing this remote site, the vault containing the power systems, the seismometer being buried next to it below. But this is sort of the picture we want to start with. These seismic stations are capturing how the ground at this site moves all the time. And this was a picture from Alaska Earthquake Science Facts slides about the transportable array and really standard station design now in Alaska with a lot of different equipment being recorded. But mainly we're looking at solar panels and a box to contain the power systems. The seismometer is, in this case, shown as buried in an 8-foot borehole next to the station. There are other things. What we see, the BGAN satellite antenna, that has to do with telemetry, getting this information to places that can use it. This seismometer is not very useful if the data are just sitting here. That information can't be used unless it's transmitted by satellite to a data center. So this shows the sites for Alaska, kind of custom designed to withstand the tough conditions in Alaska, from bears to weather to low solar and cold. Here's a shot advertising the kind of geophysical entities that reside on upper campus here at University of Alaska Fairbanks. And if we want to focus in on just two of these, the seismic data acquisition going into the Butrovich building where we have high performance computing is shown here. I am in the Geophysical Institute here on the 4th floor, and on the 3rd floor is the Alaska Earthquake Center, really the center of operations for managing the 50,000 or so earthquakes that are documented and each year in Alaska. So this shows kind of where these physical entities are, with the digital data streams coming in here, coming over here, algorithms running, and people sitting in desks and reviewing this kind of information here at the Earthquake Center. This is a shot from the Alaska Earthquake Center. These computers display real-time ground motion from hundreds of stations in Alaska. Each one of these little things is a different station ordered for. As different earthquakes come in, they get sorted in a way that makes it easier to view. In reality, this is a kind of a public-oriented display, or where anyone can walk in and kind of get a really big overview of information. In reality, analysts may have their own screens and subsets of data in their own office, but this is a really nice picture of all the kind of information, maps, the latest earthquake coming in here from the Aleutians, for example. And this just shows a blow up. So these are different stations of, and this is the information. Likely you can almost see here the P wave and S wave, or potentially a couple different earthquakes coming in here. And so this latest earthquake would have occurred within a couple minutes earlier, tens of seconds to a couple minutes earlier of when this photo was taken. It shows the event here and stations in Alaska that are recording that event. So first, some very basics on locating earthquakes. First, with the triangulation method. This is kind of the standard approach to teaching how earthquakes are located in seismology. The key principle is that there are two types of waves that travel in the solid earth. There's a P wave, which is faster, and an S wave, which is slower. So within the solid earth, these what are called body waves, there's two types. So from one earthquake, both of these waves will travel. And so you'll have information coming at different times at a given station from the same earthquake. What is needed is that we need seismic wave recordings, or seismograms, from 3 stations to locate an earthquake. And each recording must contain clear indications of the P wave and S wave. There's a lot of things recorded by seismic stations, all kinds of activity, from cars driving by, animals, things in the atmosphere. But what we're looking at is something that has clear P and S waves. What is assumed in this process is that the speeds of the P waves and S waves are constant everywhere on Earth. This isn't entirely true, but it works fine. The Earth has a lot of variability, so these waves don't actually travel at constant speeds, but we can use some approximation to get an idea of where the earthquake is. And so what that means is that the earthquake to station travel time of waves will only depend on the distance between the earthquake and station. So we don't, at the outset, when we receive these different P and S times, we don't know how far the earthquake is away, but we'll see how we can use this information. Also assumed is that the earthquake originates at or near the surface of the Earth. This can be modified to consider earthquakes deep in the Earth, but for the sake of this triangulation method, it's probably easiest just to think that the hypocenter is the epicenter, or they're just at the surface or close to the surface. So you can look at an animation from YouTube showing what the P wave motion is. And what you can see about a P wave is that if you're a particle or a piece in here, that you move in the same direction that this wave is propagating. So if we try that again. So the particle motion is parallel to the direction of the wave propagation. The wave is propagating in this direction, and if you were in this little block, you'd be moving in the same direction of the wave propagation. And that contrasts with the S wave. So here with the S wave, the wave is again propagating along the length of this prism, but the particle motion is actually up and down. If you were sitting on one of these blocks, you'd go up and down as this wave went by. And so that is an S wave, and that travels slower. Watch it again. The S waves are always slower than the P waves. All right. And so these two waves are the information that's used to locate earthquakes. So here are some real examples for 3 different stations for the same earthquake. And we see, you have to kind of blur your eyes, but basically there's a start, which is the P wave, P wave, P wave, and the P wave here. And then there's expected to be an S wave, and it's kind of hard to tell, but here's the start of the S wave. You can see kind of larger amplitudes here. And then here's the S wave coming in right here. Sometimes they'll use, instead of the vertical component, they might use a different component where it would be more obvious than the ones shown here. But here's the S wave, and then here you can see the start of the S wave. And so the measurement that's made is actually the time difference between the P and the S wave. So here it's about 2 minutes, here it's about 35 seconds, and here it's about 20 seconds. The distance shown here, we'll see how that distance is determined. But for now, the measurement is just a time difference between where the pick for the P wave starts and the S wave starts. And so we saw that the assumption is that the S wave and the P wave, that the travel time from the event to the station only depends on the distance that the station is from the event. So these are curves that show, in this case, the slope of the curve gives some idea of how fast the wave is. So the P wave here travels faster than the S wave. And the measurement that's made as an example here is the difference between the S and P travel time. The S time comes later, the P time comes sooner. And the difference here, as an example, this would be 5 seconds. This is the measurement that we make off the seismogram. And it tells us that the earthquake is 40 kilometers from the station. It doesn't tell you what direction it is. It just says 40 kilometers away from the station, this earthquake occurred. That's super useful information. And we'll see why we need 3 stations to get a little more precise on the statement about where the earthquake is. So from that, we also get information that the P wave arrived 7 seconds after the origin time, and that the S wave arrived 12 seconds. We could use that to actually calculate just off this plot what the slope of the line is 3.3 kilometers per second speed for the S wave. And here the P wave gives 5.71 kilometers per second. So the measurement is shown here as the difference, but you can also think of there being sort of a travel time of 7 seconds for this particular earthquake for the P wave to arrive, and 12 seconds for the S. 12 minus 7 gives us 5. And so this is how we get a distance from the S minus P travel time gives us a distance. And from that, we can go find where these Clear Creek Butte, Valdez, Aniakchak volcano go on a map. From those stations, we can draw circles that have a 500-mile radius here, 215-mile radius around Valdez, Clear Creek Butte, 115 miles. We draw circles. And if all things are measured pretty well, then we expect these circles to intersect at one point. And you can see if you only have 2 circles, you can narrow it down to 2 possible places, here or here. But if you have 3 circles, you can isolate, it'll collapse onto 1, and we get an idea of where this earthquake is. So from each station, from the seismogram, we have an S minus P differential time. And from that, on the graph, we can determine how far away the earthquake is from each station. And by drawing these circles, gives us this, in some sense, from each of these 3 points form a triangle, but we can determine where the epicenter of the earthquake is. And there, all we've used there is the S minus P arrival time on 3 stations to locate an earthquake. The second sort of very basics part is the notion of signal and noise. The seismometers are recording ground motion all the time. And some of that is just noise. It could be meteorological, all kinds of things. There's always information. And so when we have earthquakes, as shown here, we talk about the signal to noise ratio. And that is the ratio of how much bigger the signal of the earthquake is relative to the background signal of the noise. So that's what is meant by signal to noise ratio. And this is showing 2 different earthquakes that have different signal to noise ratios. This would have a larger signal than this one. And this concept is necessary for how computers automatically detect that there might be an event on a particular live recording of ground motion. Okay, moving on to how computers detect and locate earthquakes. So these are 4, 5, and 6 are really looking at the computer and automated portion of this. This shows a recorded seismogram, and this information can be through data processing. You can look at sort of like what's called a short-term average divided by the long-term average, of the background amplitude. And so this seismogram gets translated into this, what's called an envelope. And we're looking at places where this value exceeds some sort of background level, like signal to noise. And during that time, the computer will say detection on, detection off. Here's the second detection on, off. And so as it says here on the left, this algorithm is looking for signals that stand out from the background. And this is the starting point for thinking about, were these earthquakes? Are there other stations nearby that have detections as well? Or is this just isolated to one particular station? If the entire state lights up with these detections, then chances are, well, you've got an earthquake, ground motion affecting all of Alaska at once, very likely to be an earthquake. This shows stations, BPA, CAS, CHUM, KTH, stations in or near Denali State Park showing 24 hours of detections, these R's and P's and arrivals. As it says, not all detections become arrivals since some cannot be associated into valid earthquake events. So this shows this automated procedure, lots of, just for a small subset of stations over 24 hours, question of, how many of these P's, if they all line up with 5 different stations, then that's probably, an event that's common to all of, if all those stations and more. These are examples of seismic signals routinely detected by the automated system. Here's a real earthquake shown at the top. This is a noise signal, non-earthquake signal, medium duration, could be a car driving by. In this case, here's a non-earthquake signal, short duration, small amplitude. Here's a data glitch that, you have to have computer algorithms and review processes to make sure you don't call this an earthquake. What's characteristic here is how quiet, there's nothing here. And then all of a sudden, boom, an abrupt change in this ground motion, a very large signal. So this is the kind of signals that are most relevant and important for characterizing earthquakes across the region. Here's an example of the kind of visual graphics that analysts see and how the computer is working as information comes in. Here's less than 1 minute after this earthquake in 2019. This is showing just an example of how many stations are available, 24 different arrivals, less than 1 minute after the earthquake. The computer has a pretty good idea of where this earthquake is. 62.8597 latitude, minus 148.8852 longitude, depth of 59 kilometers, most likely in the downgoing subducting Pacific plate here. And so this is trying to show, as time evolves, different information comes in, and the estimate for where the location and the origin time. So this is the origin time. You can see it doesn't change much overall. And this shows latency, says, how long it takes to get this information. So 53 seconds after the event, we've got what appears to be a pretty good estimate for the location and origin time. 1 minute and 16 seconds. There's now 49 because it takes time for these information to reach the stations. So the farther stations, the information from the farther stations simply takes longer. The waves have to propagate out there. That information gets broadcast to the data center. So you can't use the information from very far away, at least until the information reaches those stations. That gets broadcast. And so after, this is with 49 arrivals, you can see that things have changed slightly. The depth went from 59 to 52 kilometers. And the final event detection with 63 arrivals was 6 minutes and 30 seconds after the earthquake. From all this information, this would be the most refined, with taking into account the most information available. So this would be an example of very good data coverage and giving you an idea of how many minutes it takes to get a final or best solution. This is prior to any analyst reviewing these. And for details on the program and algorithm, this is the published paper, Generalized Earthquake Location Package. You can dive into that if you want more details on, having a good algorithm from the information that you have. You want to characterize what you think the source is, but also the uncertainty, the variability in that estimate. For decision making, you want to know, things like uncertainty are very important. So here we are down toward the bottom of the list. This is with the computer detection, but then there are analysts who review the arrival time picks that the computer has done and the hypocenters and origin times that have been determined from the computer. And there's some iterative refinement there saying, oh yeah, they missed that. This computer accidentally picked this, or the algorithm wasn't quite correct. So humans step in within minutes. A duty seismologist, someone always is on duty for any earthquake and starts looking, was this a major event? What is needed here, especially for the larger events? And within days, a staff seismologist would be looking through hundreds of earthquakes are happening per day, and there are hundreds of stations per earthquake. So it's a huge effort to just review the volume of data to keep the quality of this final product as high as it is. This is just a shot of, here's a seismologist on duty with the phone, laptop set up, showing latest earthquakes. And when this thing goes off, it's almost like a doctor on medical duty. You have to be ready to respond and take action. And really, this is all aimed at trying to understand what all the dots on this map really are and where they come from. This is a 2021 seismicity map, likely something on the order of 50,000 dots on this map. And each dot was determined through the procedure we just looked at of stations all over Alaska, in particular ones that are closest to each of these dots would be providing information about P waves, S waves, their travel time differences. We didn't talk about the magnitudes of these events, but from just the arrival time alone, we can get locations for where these events are. And it involves a lot of data, a huge amount of effort to keep these stations live and running, computer programs, constantly streaming and analyzing all the data coming in, and analysts reviewing all this content to bring together this final really spectacular view of just what 1 year in Alaska looks like. That in this particular year, magnitude 8.2 earthquake, 7.9 aftershocks, all kinds of exciting events happening in any given year in Alaska. So takeaway topics: seismometers all over Alaska record ground motions constantly. These ground motions are transmitted as digital signals to the Alaska Earthquake Center. AEC computer programs detect P waves and S waves and then automatically locate earthquakes and determine their origin times. The analysts review automatic data, refine measurements, and improve the earthquake locations for the final catalog. Thanks for watching. And as I mentioned, the videos, content here, and text mostly available from the Alaska Earthquake Center. You can follow some of these news articles in more detail shown here.